In this video, we will study the dynamics of electricity. In our previous video, we studied the electrostatics, means electricity at rest, and we understand that if we have two potentials, then we can always provide the potential difference, which is already the voltage. So voltage belongs to the topic of electrostatics. Now, in this video, we will now study or analyze what will happen if electrons move. So therefore, we call that as the current, the electric current. Okay, so what is electric current? Suppose I have a battery, and we understand in a battery we have two potentials. We have the positive potential and we have the negative potential. The positive potential is the high potential, and we have the low potential for the ground. So usually ground is 0, and we have this as the maximum potential. So we have now the potential difference from A to B. So we call this as the electrostatics. We have the voltage within this cell. This is a dry cell. Okay. So therefore, if we connect this with a load by means of conductor, a wire conductor, suppose we connect one line of that to the one line of the bulb, then another line from the high potential towards the another terminal of the bulb, then this bulb will light. Why? Because we have a special material here called as filament, and that filament is very sensitive to the current. So the moment that this filament feels current, then it blow, it glow. So once glow, then we have this the reflection of uh, the metal, the filament which now experience the current, then it will convert to light. So if I connect this one, then it will produce light. So therefore, the light is actually a function of intensity. The greater the intensity means the greater the light or the brightness is increasing. And that intensity is a function of the current. So the greater the current, the greater the intensity of the light. So where is the current uh, pass through? Now it passes through the filament of the bulb. So the moment that the filament again experience or feels the presence of the current, then this will glow. Again, this will provide light. So in this circuit, now this is now a closed circuit. Therefore, we call this as dynamics of electricity. Means electricity in motion. So in this topic, the electric current is the first topic of the dynamics of electricity. So electrons, take note that the electrons will travel from low potential towards the high potential. And the reverse of this, because the moment that the electrons will travel, then there must be a current in opposite direction. So this is the current, and this is the measures of the amount of the electrons traveled per time. So the motion of the charges per time is actually the current. But the reverse direction, this is the conventional flow of electric current. It should be coming from the high potential towards the low, while the electrons coming from the low towards the high. But the amount of the current flows into the circuit is the amount of electrons that travels into the conductor. Okay, so therefore, if we remove the wire, then we close the or open the circuit, which means that there is no motion of electrons. So if there is no motion of electrons, there is no current, the electric current. So what is electric current? Okay, that will be our task for this module. So how to compute the electric current in terms of the load, or maybe it load in terms of the conductor. So in this module, we'll focus on the electric current that passes through the conductor. Okay, so this is just like water that flows into the pipe. So current is in this direction. Then as it passes through the filament, it should be in this direction. Then follow the conductor, then move downward. It's against the flow, and we have this as the I. Now take note that in electricity, we understand that is the motion of electrons. But regardless of what particle is moving, whether electrons or protons, the current is always towards the low potential. Okay? It's just like gravity, that when you release an object, it will move towards the low potential energy, and which the low potential energy will be the ground surface. So again, regardless of what type of electrons that travels, whether it is electrons or protons, then current will flow from high potential to the low potential. Okay, now there are two kinds of uh, current. We have the steady state current, which means that the current does not change with time. So if you wish to calculate the amount of the steady state current, it's simply as Q over T. The charge, which is the moving charge, divided by the time of travel, is the current. The analogy of this is the velocity of the water that into the canal. Now, take note that the water molecules moving downstream. Now, if we measure the displacement of that water molecules with time, that's velocity. Now, in this case, the flowing is not a water, it is electrons. So, therefore, if we want to quantify how many electrons do we have for a given time, then we are quantifying the amount of charge per time, and the result will be the current. Okay? So, this is steady state because it won't change. The charge does not change with time. But if the charge changes with time, then we call that as non-steady state. So that's the case. We will use the infinitesimal value. So your Q now, because Q is not a constant, therefore it might be the charge changing with time. So we will use dq, and we have the dt. So dq, small letter q, means this is an infinitesimal charge at that point per time interval infinitesimally, then the result is still I. Okay, so there are two ways to calculate. Because if the condition is steady state, then use this formula. If the condition is non-steady state, which means that the charge with time, depends with time, then the current also depends with time. So therefore, in order to calculate, we use the dq over dt. This is a differential equation. Now, what will be the unit of the current? Now, as I've said, if you are asked what is the unit of that physical quantity, we need to use the definition of that quantity. Now, the current, remember, by definition, is charge per time. Regardless of steady state or non-steady state, this is charge per time. So, therefore, asking what is the unit of the current, then go with this definition. What's the unit of Q? Coulomb. The unit of time, seconds. So, therefore, the unit of current should be coulomb per seconds. Okay? But, coulomb per seconds means ampere. In honor of Andre Marie Ampere. He was able to discover current within the circuit. So, the coulomb per second means ampere in this I, or simply as big letter A. Sometimes books we use EMP. EMP, amp. Okay? It's the same as ampere or big letter A. So therefore, we can say that the 1 ampere unit of current is equivalent to 1 coulomb per seconds. Now, take note, ampere is SI. Coulomb per seconds is also SI, but we use the ampere for simplicity. Okay? So, therefore, the unit should be amp, EMP, or big letter A for the unit of current. Now we have two types again of the current. We have the so-called direct current, or we call this as DC current. Now DC current or direct current means this is a one directional flow, which means that uh, electrons will move only in single direction. So it is coming from low to a high. Okay, which means that okay, electrons will travel from low to high. So in this case, since this is always high and this is always low, so the flow of electrons is one directional flow. So we call this as DC current. This current is a DC current. Why? Because the source is a DC source, DC voltage. So the symbol of the DC is actually a polarized supply. So we have the identified positive. This is always high and this is always low. So therefore, electrons will travel in one direction only. Now another type is we have the this is not direct. This is alternating current. Alternate current. I will change this one. This should be alternate. When we say alternate, this is a kind of directional two directional flow means okay, this is alternate current. So therefore uh, in this, for example, this is an AC source. This is alternate current, which means that this A can be high, can be low, and this B can be high, can be low also, which means that there are cases na this is high. So if this is high, this is automatically low. If this is low, automatically B becomes high. So in that case, the electrons travel in two directional flow. Okay, look at this one. This is now from A to B, and this is B to A again. So electrons will keep on changing its direction. The frequency of changing direction is, we call that as uh, the frequency of the current. Okay, so the symbol for the AC is we have only one wave. This is two waves, means we have the positive and we have the negative. So this one is only one. So therefore this is ACB. ACB means alternate current voltage. ECA means alternate current. The unit is ampere. Sometimes, so therefore this one is positive. Okay, so positive, sometimes we call it as BCC, and the negative is ground. Okay, so these are the two types of current. So therefore again, in short, in DC we have only one directional flow, and the current is from high to low. Take note, we in our study we will not use the electrons that travels. We will use the current that flows from high to low, means from positive towards the negative. And there are two types. We have the direct current and we have the alternate current. So this is now AC. So change this to AC current. Okay, so going back to the question is how much current? How much current in a wire conductor? So this red lines and black lines are the conductor. So I use the red. Why? Because this is from the high potential and this is black for the from the low potential. But these are the same wire. So when we say wire, it has the area. So the question is how much current can be measured from the wire conductor. So to answer is we need to consider only segment of this. What will be the current that passes through this wire? Okay, so take note that it is not only one electrons. Electrons are very small particles. So when we say part of the wire, there are millions or thousands of electrons for that small distance considering the conductor. So therefore, the question now is how much current within this segment. Okay, so take note, I is what? Q, the number of charge inside this element for a given time is the current. So therefore, look at this one. When you look at closely to this a very very small segment, this will be the behavior. So suppose there is no supply, so current is zero. But even if the current is zero, because metal, the free electrons keep on moving in all directions. So electrons did not at rest. It is always keep on moving. Within the metal, the free electrons keep on moving. This in all directions. So they will collide to each other. So in this case, our current is zero or if we have no charge. So when you look at I have here an example of the one. I have an example of the electron. So therefore, if we have this supply, then these electrons will travel with direction, and it follows to the conductor, just like water that flows into the pipe. Okay, so therefore it will move in this direction. It will move in all direction, but moving in all direction is keep on changing its position. Therefore, we call that as a drift velocity. So therefore, suppose one electron here, we will analyze only one electron. Start at that point, this is the path of the one electron. So then it moves. Then while moving, because of the supply, it will displace as a certain distance. We call this as the displacement of one particle. So with time again, it will move. Okay, it will move. So therefore, this is now forming current. So take note, we have this velocity. We have this velocity of one or single electrons. We call that as the drift velocity. V sub d is the drift velocity. Means it is the velocity of one particle, charged particle, which is electron or maybe a proton. Okay, so take note that the sizes of all the electrons inside are the same, identical. They are identical in size, meaning same mass, same structure. Then its velocity also, even if there are, this is anywhere the electrons will travel within the metal, but the magnitude of velocity are the same, which means that one particle here has the drift velocity, but the drift velocity is in line with the conductor. So this is the motion of one particle, but it will keep on moving with the we call this as translational motion. So again, it is because of the drift velocity. So therefore, each particle here has the drift velocity, which is in the direction of the current. So the question now is, how much is this current as a function of drift velocity? And take note that this is conductor, so we have this area. So the question is, how to calculate, our task is how to calculate the current as a function of this drift velocity and area, and also the kind of material. Because take note, we have the conductor. All metals can be a conductor. We use always copper in our household electrical installations because copper are affordable. Okay, so therefore, different materials might have different current because it depends upon the number of electrons within the metal, because different metals have different number of free electrons. Okay, so to answer this one is we need to consider a very very small. We have to consider a very very small thickness of this. So if this is a very very small again, okay. So by the way, we have this we have this depth velocity, okay, for every charge. So What is I? I is dq over dt. So therefore, in order to answer this question, we need to find the dq and we need to find the dt. Okay? So, dt or dq, so we will consider a very, very small volume. So, suppose we have this as the displacement of this particle, a very, very small displacement of this particle traveling within the conductor, so call this as ds, so infinitesimal displacement. So we will consider only one part of that, so therefore this is now a segment of the conductor whose length of that segment is ds, and we have the area of the conductor. So we call this as the, in order to compute for dq, because we want to calculate I, so meaning we need dq and dt. dq, which means that in a very, very small volume, this is a very, very small volume, how much charge inside of this a very, very small. So that's dq. So to answer is, take note that we don't know what are the numbers, how many electrons are there inside that segment. So to answer the dq, take note that one charge of electron is q. So therefore, this electron, the charge is 1.602 times 10 raised to negative 19. Now, we need to multiply that because we don't know the number, and we all know is the volume. We don't know the number, but we can evaluate this because we have this volume, area, and we have this length. This is the volume. We call this as infinitesimal volume. So if you multiply the infinitesimal or segment of volume, if you multiply this volume with Q, okay, so therefore, we are now on the way to count how much charge inside to the segment. Now we have one thing to multiply. We have the charge concentration. What is charge concentration? The charge concentration is, we assign this as N. This is quantifying the amount of electrons per volume. This is per volume. So in a copper, we have the charge concentration of copper. In silver, we have another charge concentration. Now again, charge concentration is quantifying the amount of charge per volume. Per volume. So the unit of charge concentration should be per volume. We will multiply that to the volume of segment and the charge of one of single particle, which is the electron. So take note that the unit of volume of segment is cubic meter, and the unit of the charge concentration is per cubic. So therefore, the unit will be cancelled. The cubic meter will be cancelled. And we take note, we multiply that with a single charge. So the unit of charge is coulomb. So therefore, the dq should be the coulomb. Now, if we will not multiply the charge concentration, and you are multiplying the charge element with the volume of segment or infinitesimal volume of the conductor, then you did not come up with a unit of charge. So therefore, the process of calculating dq is the charge of one particle. Okay. Now, supposed to be, you have to multiply the number here. Again, we don't know the number of this electron, so all we know is the volume segment. So, you need to multiply the volume segment multiplied by the charge concentration. Sometimes we call this the density of electrons, counting the density per volume, or the amount of charge per volume. But this is only per volume. Okay? So, therefore, mathematically, your dq now becomes q, which is the, what is q? Q is the charge of one electron or maybe proton multiplied by the volume. Volume is just a container, so it is an empty. So in order to fill up with charge, then we will multiply n. N again is the charge concentration. This is now in the presence of the electrons. Remember nga, different materials have different charge concentration. So multiply that with the volume, then the volume now contains the charge. Pero take note, this is 0. Oh no, the unit should be cancelled because it's volume and this is per cubic meter. So therefore, again, this is charge unit. Okay? So therefore, from a single charge, we integrate that by multiplying the volume with the presence of electrons, and it is based on its density. Okay, so therefore continue. What is volume? Look at this one. Geometry says that the volume of this element or segment is the area times ds. Okay? So substituting the dv with A, ds, A, which is the area, times ds, is now the volume. This is dv. Okay? Now what is ds? Now ds in terms, because we will incorporate the direct velocity. So we will eliminate ds and we will express this in terms of what? In terms of direct velocity or vd. Now take note, the definition of what? The definition of velocity is s over t. Take note, s over t. So therefore, s over t, v is s over t, close diagonal. So therefore, it should be s is equal to vt. So therefore, if you wish to calculate how much is this distance, how much is the distance from this point towards this point, simply multiply that with the velocity. This is constant velocity. This will not change. So the constant velocity, the velocity multiplied by time is the distance of the distance traveled of the particle moving from this point towards that point. Okay? So therefore, dA should be what? The drift velocity times the time. Okay. Now what is now the result? Okay, so therefore, all you need to do now is divide both sides by dt. Okay, divide both sides by dt. So therefore, in this turn, this dt will be cancelled, but the dt was transferred to the denominator of dq. So dq over dt is equivalent to nqa dv. The charge concentration, the charge of single particle, it is the electron, times the area of the conductor, times the drift velocity is dq over dt. But dq over dt, take note, is, look at this one, I. So therefore, it answers to our problem. How much current in a wire conductor? The answer is I is equal to nq avd. So therefore, it should be the number or the charge concentration times the, we call this as charge of the particle. This is only single, take note, single charge only. So it can be the electron. And we have area times dv. Vd, the drift velocity. Area of the conductor. By the way, Q is, take note nga, if we say electron, the sign is positive. Now take note, as I've said, regardless of what kind of charge is traveling, whether electron or protons, the current still in this direction from high to low. So therefore, this formula should be what? This Q should be an absolute value, which means that do not include the negative sign of electrons, or you cannot also include the positive for the proton. So regardless of what kind, because this is an absolute value. Okay? So I, now, how to calculate I? Multiply the number or charge concentration or the density, the compactness of the electrons within that metal, then multiply it with the electrons charge, and multiply it with the area of the conductor times the drift velocity, then the answer is I. Now look at this one. Take note that I is measurable because we have the current, we have the ammeter. The ammeter is a device that measures current. So therefore, by experiment, this can be measurable. This N was measurable also because there are in table constant. The charge concentration per metal was provided already by experiment. So these are available. This charge particle is, if we say that electron travels, then we have the charge per electron. But take note, even proton, the charge of proton is the same as the charge of electron. So therefore, regardless of what kind of charge is that, but as long as it is a single charge. then area is measurable because this is the area of the conductor. This one is not measurable, the drift velocity. So in other words, through experiment, we can always solve for the drift velocity by what? Dividing both sides by NQA. If you divide both sides by NQA, then it is the drift velocity already. So remember this relation. This is a very important relationship. Okay, so where I is current, electric current A, and N is the charge concentration 1 over per cubic. Take note, look at the unit. N. N is per cubic. There is no unit in the numerator. So this is just per cubic. So there should be a number. There should be a number, which means it is the number of electrons per cubic. But a number has no unit. Okay? So it should be per cubic. And the Q, take note, this is the charge of a single particle. Single particle. So electrons, 1.60902 times 10 to the 19. Protons, same charge. Okay? Unless, by the way, if we don't know, if the problem does not provide this Q, now analyze the problem if it is the electron that flows or it is the proton. But take note that they have the same charge. Now some problems also, they provide the single charge particle, so use it. If the problem says it is a charge particle, single charge particle, okay? A is the area of the conductor. The unit should be meter square. And the drift velocity VD is meter per second. Sorry, this is meter per second, not meter per second squared. So this should be, eliminate this one. Okay, so now look at this one. If I divide, look at this formula. If I divide both sides by A, what do you think? What will be the result? Okay. If I divide this by A, so therefore this will be cancelled out. So what will happen is we have I over A, okay? I over A in QVD. Now the I over A is the current density. This is another physical quantity. This is vector, okay? Current is not a vector, but the current density J, big letter J, is a vector quantity. So the unit should be what? The unit should be, by definition, this is I over A, so this is ampere per meter square. This is the unit of current density. So in this case, because the particle is moving in this direction, so therefore the current density also in this direction. And this, take note, this one is the amount of flow. Okay, so the vector is the current density. So therefore, the current density can be expressed in terms of the charge concentration and the single of the charge, and we have the drift velocity. So therefore, this is J. So therefore, J can be calculated by NQVD. If you multiply this with A, the result is I. Okay? If you multiply this A. If you divide by this one by A, the result is J. So therefore, what's the difference between the one? What's the difference between the current and the current density? Again, the difference is, one is current density is a vector, okay, while the current is scalar. Then the density is the ampere per meter squared. So therefore, it should be the current that flows per area. Okay, so that's it. I over A is the current density. So in order to practice, we have this problem. We will solve this problem. A silver wire whose diameter is 2.6 mm transfers a charge. Take note, transfers a charge of 420 coulomb in 80 seconds. So what do you think? What is this? What kind of given is this? Charge Q. Okay? But take note, this is not a single particle. It was not stated here that this is a single particle. it says that the silver wire 2.6 is the indicator transfers a charge of 420 coulomb in 80 minutes. The silver contains 5.8 times 10 raised to 28 free electrons. Okay, this is per cubic. So this is now what? This is charge concentration. This is in. Okay, in, because why? Look at the unit. Look at the unit. This is per cubic meter, and these are the number of electrons. Okay. Now, what is the question? Letter A. What is the current in the wire? If the wire is 2.6 mm diameter, and it is a silver, take note, it can be copper, but this time is a silver. So the charge concentration is 5.8 times 10 to the 8. How much is the current? Okay. So what will you do? Now, the answer is, take note that this charge does not change with time. This is 480 in 80. 420 in 80 minutes. So therefore, to answer this question, is use the steady state formula. The Q over T. The Q over T, which is I. So substitute the values. The Q is 420C divided by 80 minutes. Okay, so take note, this is big letter. This is not small q. This is big letter Q. So take note that the unit is inconsistent. So we will go with SI. So the unit should be ampere. The 1 ampere. What's 1 ampere? Ampere is 1 coulomb per second. And this is coulomb per minute. So all you need to is to convert the minutes into seconds by multiplying 60 seconds per minute. So this will be cancelled. So we have now coulomb per second. So the answer is 0.0875 amperes. So this is the answer for letter A. Letter B. Letter B is what is the current density. Okay, what the current density? It is J. J is I over A. Take note, we have already I. I is given, so all you need to do is to divide that by A. But what is A? The area of the conductor. Area of conductor was not provided in the problem, but instead we have its diameter. Now, if diameter given or reduced, we can always calculate the area of the conductor. Take note of the square as a circle, because diameter means the cross-section of the conductor is a circle. Sometimes square, sometimes triangle, but this one, because given the diameter, automatically the area is a circle. So therefore, in letter B, J can be calculated by dividing the I with A. So what I is equal to 0.07875 A. Then area is pi d square. Pi d square over 4 because diameter is given. Okay, look at this one, 2.6 mm. So we need to convert this for consistency. Convert this to meter. So this should be multiplied by times 10 raised to negative 3. Then square it. Then divide by 4. Okay? This is the formula of the circle, pi d squared over 4. If it is reduced, pi r squared. Okay? Because r is d over 2. So it should be pi d squared over 4. So, use your calculator and the answer is 16,480.54. The unit, take note of that, ampere per meter square. This is the current density. Letter C. What is the magnitude of the drift velocity? Okay, look, this one. You are now asked, take note. We cannot see the electrons that travels through the conductor. We cannot see in our naked eye because it is a microscopic, but we can calculate theoretically the speed of the electrons that moving around inside the translational motion of the electrons inside the conductor. So it is only the theoretical idea that describe the velocity of the electrons travel inside the conductor. So we call that as a drift velocity. So take note of this formula. Look at this formula. This is the drift velocity. So you are asked to solve this one. What will you do? Divide both sides by NQA. Okay? Or you can use it in terms of the current density. So we will use this one by dividing both sides by NQA. So we have this one. But take note, I over A is J. So you can, but this one we can use this current divided by N. N is given. Q is, what is Q? What is Q? Now take note, this Q 420 is the charge, the entire charge. Calculating, take note, this velocity, this drift velocity is not the velocity of the entire. It is the velocity of that single electron. Take note, the motion is look at the particle is electrons, because you are using N, and this N is free electrons per cubic meter. So therefore, we are talking of electrons flowing in the silver wire. So therefore, do not use, reminders, do not use the 420. Why? Because this is not a single charge. The single charge is electron. And how much is the charge of the single electron? Okay? It is 1.602 times 10 raised to negative 19. So therefore, do it. I is 0.0875. Okay, then N is 5.8 times 10 raised to 28. And this is 1. Sorry, this is 2. Replace this with 2. This is 1.602. Okay, times 10 raised to what? Raised to negative 19 coulomb. And this one is the area of the circle, the same as this one. Okay, actually, this 0.0875 that divide this one is already this one. So meaning we can eliminate this and replace this with 16. So use your calculator. Then the answer is 1.78 times 10 raised to negative 6 meter per second squared. These are the answers to the questions. Okay. So one last problem. The problem says that the current now varies with time. So therefore, this is no longer steady state. This is non-steady state. Why? Because the current varies with time. And in fact, it is given in the problem that I is 55 ampere. This is ampere A. Minus, this is the relation of the current with respect to time. So therefore, the I is keep on changing with changing time. And the relationship provides 55A minus 0.65A per ampere per second squared multiplied by T squared. So the question is, how many coulomb of charge passes through the section of the wire in the time interval between T is equal to 0 to T is equal to 8? How will you answer this one? Letter B. What constant current would transfer the same charge in the same time interval? So, what does it mean? Using this interval, how much is the steady state current if you consider the same interval? So, we will answer first the letter A. How many coulombs? So, the question of how many means, what is Q? What is big letter Q? That passes through a segment. It is not a single Q. It is the big letter Q. How many coulombs? Because the question is how many coulombs. So therefore, it should be the big letter Q. It is not a single, because if it is how much is the charge of a single charge, then that's it. But this one, how many coulombs of charge pass through the section of wire? So solve for Q. So where did you see the what relation that involves Q? Okay. Now take note that we cannot use the steady state. Again, the Q over T cannot be used. Why? Because this is varies with time. So we will use the steady state formula. And take note, this is a differential equation. We will cross the diagonal product. The diagonal product dq is equal to it, where I is the current, dt is the infinitesimal time, dq is the infinitesimal charge. Now I, take note, is given the relation. So replace I here will resolve this one. So this one is I actually. We replace that with I relation. So again, we want to solve for what? This is a kind of differential equation. So in order to take note, this dq is a very, very small charge. A very, very small. This is not a single charge, but this is a very, very small charge. Infinitesimal charge with time. So if you can integrate this, the result becomes the entire charge. Okay? So the only way to do it is to integrate. Integrate both sides. So if you integrate both sides, you are integrating dq. The limit now is from 0 to big letter Q. Why? Because we want to know how much charge. So it should be from 0 to Q. While this one, because the differential, okay, infinitesimal value is dt, so it talks with time. So the limit should be what? From 0 to, because the time start from 0 to 8 seconds. So therefore, this will be the result. The integral of dq, this is from 0 to big letter Q. This is what we want. This is our target to solve for Q. Now, integrate this opposite side. It should be from 0 time to 8 seconds because this is talking about time. The infinitesimal is time. So, use your ability in the integration. Yes, this is simple integration because this is a sum rule. Use the sum rule. There is no presence of t here. So, therefore, the integral of this is 55t. While this one is, by the way, you can ignore this unit. A and A's are just units. So, you can eliminate that. Ignore that one. So, what is the integral of 0.65t squared? Power rule. Add 1. So, add 1 with square. So, it should be 3. Now, whatever the result will be the denominator. So, it should be divided by 3. So, the result is, it should be 55t. Okay. Then minus 0.65t cube over 3. And the limit is from 0 to 8. So, evaluate the limit. We know already how to evaluate. Okay. Okay, so I forgot to, you have to enclose this one. That one. Okay. This is the upper, substituting 8 to the what? To the t. This is 5t, so replace 8 here, replace 8, then minus, replace 0, 0. So this one will be the whole term in the subtrahend a equal to 0. This is 0, this is 0. So therefore, evaluate again, and the answer says that it is 330 coulombs. This is the charge that pass a cross section of the wire. So therefore, these are the number. The question, how many coulombs? The answer is 330 coulombs. In what? From 0 to t. Time. Okay? So therefore, this answers to letter B. What constant current would transfer the same charge? The same charge, take note, the same charge is 300. So therefore, we will use this one, 330. Okay? In the same time interval. So therefore, because this is a constant current, so use this formula. Now, this time we have already this value. This is 330. And this one is the time interval from 0 to t. So all you need to do is to divide the 330 by 80 minus 0. The final minus initial time. So therefore, the answer is 41.25 amperes. This is current, constant current transferred to the wire. Okay? So, these are the solutions to this problem. Now, for your practice, this is a good example for you to solve. Try this. Try this. Okay? So, that's all. Thank you.